Welcome everyone to this tutorial. Today we will be looking at transfer learning. So, uh, as you have already seen that graphs are a very natural representation of materials, okay? And we use graph neural networks for various property prediction tasks like energies, forces, or any other material properties like mechanical properties, shear modulus, bulk modulus, electronic properties like band gaps, etc. So you can predict any properties with your structure as input, okay, and the framework is graph neural networks. Now the problem with GNN is that if you have a small data set, GNN actually overfits pretty fast, okay, and for an overfitted model, the problem is the model will be unable to generalize over new data points which was out of its training distribution. And this generalizability is a problem because you want a model to give new predictions on new data points which it hasn't seen before. We want the model to extrapolate, okay, but if you have a small data set, extrapolation is not possible, okay. It just memorizes the whole data set and it is unable to capture generalized patterns in the data set. And to effectively use GNNs, what you need is a very large data set. And to overcome this problem, okay, there is this paradigm of machine learning which is called transfer learning. Now, transfer learning is pretty much relevant in material science because we are technically dealing with data sets which are very small in size, okay. So there are some properties which are very difficult to compute, okay. So for one of the examples would be, say, defect formation energies. So calculating defects by DFT is a very costly calculation. So you need to create supercells with optimum spacing between defects, okay. And such costly calculations, it's impossible to create a large DFT dataset beforehand and then train your model. So transfer learning is this paradigm where what we will try to do is pre-train a model on a data set with lots of data points, okay, and use this trained model and then fine tune this trained model further on our data set of interest which has a smaller number of data points. So what we are doing is gaining some knowledge from this larger size data set and transferring this knowledge for using to predict properties in our smaller size target data set, okay. So there is some knowledge transfer, okay, and associated with knowledge transfer there can also be situations like negative transfer or catastrophic forgetting and everything, okay. So today in this tutorial we will use the align architecture, atomistic line graph neural networks, okay. And using this align architecture, what we will try to do is we will train two models, okay. Our property of interest in this tutorial is highest frequency of optical phonon mode, okay. So we will train two models. One model we will call the scratch model. So scratch model is a model that is trained with no other previous knowledge, trained solely on this highest frequency optical phonon mode, okay. We will see how this model performs on predicting on new test data sets, okay. And then we will train a model which has been pre-trained on formation energies, okay. So this formation energy pre-trained model has seen lots of structures, large data set of formation energies has seen lots of structures and their corresponding formation energies. So it has learned some structure energy relationships from that database. What we will try to do is, can we leverage this on our target datasets which is much smaller, and can we see any improvement in performance by using by utilizing this knowledge transfer or this knowledge that it has gained from the formation energy dataset, okay. Then let's start this tutorial. So first we have a bunch of imports to do, torch and CUDA. So we will just import them. We will use a seed value of one, random seed value of 1, 2, 3. So anyone using this seed value will get reproducible results. Now the test and train split is already done, okay. It's in two JSON files. So there is train unstandardized.json, there is test unstandardized.json. And the way the entries are in this inside these JSON files is that it's in a dictionary form, okay. So you have an ID which is the JID or the JSON ID, target value, property, the target property that you are interested in. For in this case, we will have highest frequency optical phonon mode, and the structures and of the material whose target property we are studying, and the structure is actually stored in Jarvis atoms format. Okay, so it's just like pi-mergeant structure object is another atoms format. So now what you can do is we will just convert this train and test JSON into data frames. Okay, so you run this block of code and it converts into a data frame. And now, as for any machine learning task, as we have seen previously, standardization and normalization is essential. Okay, so what we will do is use the we will standardize and normalize this data set using this standard scalar method in from this sklearn package. Okay, so fit transform is something that will calculate the statistics on of the train set. Okay, and then it will use that statistics to transform your test set. That was standardization. Okay, so just for a recap, standardization is shifting the mean of your data point to 0 and scaling it such that the standard deviation of your data point is now 1. Okay, and now we will do normalization of our data points. So normalization is this function where you are projecting your entire data set into a limited range. For in this case, we are normalizing all of the data from -1 to 1. You can also normalize from 1 to 0 to 1 depending on your applications. Okay, so it's like projecting the entire data set from this whole real number scale to -1 to 1. Okay, so once we have done that, let's just visualize this so it will be easier to understand what's exactly happening. So if you see the not standardized and normalized set, what's happening was your data was varying from anywhere between 0 to more than 3500. Once you have standardized and normalized it, your data is actually varying from -1 to 1, and the distribution that was actually in the original data set is the exact distribution that you have recovered in the standardized and normalized data set. So now our data set is actually ready for machine learning. Okay. Okay, so we will just update our data frames with this normalized test and train values. Okay, and now let's see how many data points do we have. So we have 1138 data points in our train set. So the thing is, in this tutorial we will be showing a small demonstrations. So we will not train on this whole data set. We will just randomly select 300 data points from this data set and then train our model. So let's try to create a data set of length 300. So since we saw that it varies from it has 1138 data points, so from index 0 to 1137 is the maximum range of all the data, and we are interested in picking 300 random points from this. So once we run this, here they have printed the index of all the randomly selected 300 data points. Now what we will do is take this randomly selected data points and convert them into this desired atoms format, which we need for training in Align. Okay, so when you run this block, it just creates a postcard files, the structure files of all these 300 random data points along with the target. So now your data set is ready. Okay, now what we do is next we will specify the architecture of the model. Okay, so how the Align model will specify all the parameters that are needed to define the architecture. So there are lots of parameters. I will not discuss all of them. You can always have a look in the Align website and see what they mean. I will just describe some of the important ones. So when you initialize a graph neural network, you will have atom features. Okay, so the features on the atoms are similar to that was used in CGCNN. So same features that we saw in the CGCNN exercise, the same will be used here. Nearest neighbor strategies, we use this k nearest neighbor algorithm to find what are the nearest neighbors. Okay, JID defines your atom ID uniquely, or your structure ID, or your entry ID uniquely. So JID is our unique key for identifying all the unique structures. Random seed is 1 to 3. We are not doing any classification. And now this block of n val, n test, n train, okay, and train ratio, validation ratio, test ratio. So you just need to fill up only 3 of them. So n is either you fill in absolute numbers, okay, that this many numbers will be used for my validation test and train set, or you specify the ratio. So I'm specifying the ratio, which is easier to handle. And now for this model demonstration, we will just showing this model with 15 epochs, okay, and a batch size of 4. And there is a learning weight decay, which is important for the optimization we are using. So some weights, they become huge over the course of training, okay, and they influence the prediction too much. So we don't want that. We want the weights to be minimal, okay, so that it can generalize better. Then we have the learning rate, okay, and the criteria for loss that we will be using is mean squared error. Optimizer is weighted Adam optimizer, okay. And other important thing that we want to show is max neighbor. So we have a cutoff of 8 angstroms and the max neighbors of 12. So the code will first check within the 8 angstrom radius of what are the neighbors. If it cannot find 12 neighbors, it will increase this cutoff till it finds a maximum of 12 neighbors. Okay, so whichever is achieved. If you achieve 12 neighbors within 8 angstrom, then it's fine. If you don't, then the code will actually increase it till it has achieved 12 neighbors. And now comes the neural network architecture. Okay, so we have 4 align layers, 4 graph convolution layers. The input dimension of our atom feature vectors will be 92, and same we will have edge features also on the line graph. So that has this embedding space that is in this embedding space of 80. Okay. And hidden dimensions is 64, and we will have just one output, which is our for our case the highest frequency of the optical phonon mode. So I will just configure this. And now to train the model, so to train the model, you have this file train align.py. Okay, so if you want to know what are the parameters that are inside the model, like inside this file, you can go to this help function, and it will actually define you everything that is inside this. Okay, so you can have a look at this. So we will start the training process, and the training configuration is so I stored the training configuration before in this config.json file. So it stored all this configuration in this, and now while calling the train align.py, I will give this configuration as input. I will specify the output directory and the number of epochs I'm interested in running this. So if I run this, we have 160 training data, 40 validation set, and 20 for the test set. These are all the parameters that I had specified in this config.json file. And now as you can see, the training has started. So the thing is, we are this align model, you can have graph level prediction and atom level predictions. Okay, so what we are interested here is only the graph level predictions. Okay, but if you were interested in atom level predictions, and if one of your interest was energies of atoms, energies of each atoms, what you can do is the gradient of those energies with respect to the atomic positions will actually give you forces, and further you can also get the stresses or any additional properties that you want to derive out of your atomic features. But as of this model we are doing right now, we are not interested in any atomic features or forces or stresses or any other additional losses from the atomic side. We are only interested in graph level prediction and graph level losses. Okay, so as you can see, the epoch 0, our initial loss was 22.305, and gradually as the epochs increase, this losses actually keeps coming down. Okay, so now our 14 model has trained for 14 epochs, and now our training is done. Okay, so this we have trained the scratch model, so there is no transfer learning here. We have taken the optical phonon highest optical mode data set, trained a scratch model, this align graph neural network model on it. Now what we will do is, we have a pre-trained model on formation energy dataset. Okay, so now what we will try to do is fine tune this model. Okay, fine tune this pre-trained model and on this on our data set of interest, and try to see if we are seeing any gain in performance of the model. Okay, so same as before, we will now train this. Okay, and we will restart the restart training from this model, which is called the current model. So this current model is the pre-trained model on formation energy dataset. Okay, so we will load this model and we will fine tune this model with our data set and run 15 epochs of this. Okay, so if I run this block now, yeah, so training has started, as you can see. Okay, so now our fine tuning is done. So now that our fine tuning is done, let us test whether we have gained any advantage by this fine tuning strategy, where we are expecting some knowledge transfer from the previous formation energy training to this phone on mode training. Okay, so now what we will do is load both of these models. Okay, and then initialize graphs. We have a test dataset JSON that we showed before, and we will use that test dataset JSON to do inference. So this time when we are loading the model, we are doing only inference and we are not doing any training. So no weights and biases will be updated during this run. Okay, and there will be no backpropagation technically. Okay, so let's run this block. Okay, and when you run this block, it just parses out all the data from the test and training set. Okay, and for each of the JIDs, you can see there are two targets. I mean, there are two outputs. So one is from this scratch model and one is from this fine tune model, and this is the target. Okay, so it's easier to visualize and to see these raw numbers. Okay, so let's first undo the standardization and normalization that we have seen before, because our data set is in a different scale now. If you want to know the actual values, we need to undo the standardization and normalization. Okay, so this block of code will just undo that operation. And now let's just analyze the performance metrics. Okay, so we just printed the scratch model R2 score and mean absolute error, and the fine tune model R2 score and mean absolute error. So look at this, the scratch model running for 15 epochs on those 300 points, your R2 score is 0.49. The fine tune model running on the same data set size, okay, has given a better R2 score of 0.65. Also look at the mean absolute errors. Okay, so this is quite large, so 206 EV. Okay, 206 in whatever units the prediction is, it's per centimeter. And for the fine tune model, the mean absolute error is 171. So there is a subsequent reduction that you see, although both these are bad, and the reason for both of them being bad is that we have ran for very limited number of epochs. So run it for like some 100 epochs and you will see good convergence and very low MAE and very low MAE scores for both of this model. But even by running this small number of epochs, we are able to show the advantage that we gained by using the previous knowledge from some other data set and leveraging that on a data set which has much smaller number of properties. So this knowledge transfer is what summarizes the transfer learning. So in the end, maybe I would like to give an analogy of this transfer learning, of how we as humans have experienced this. Okay, so one example would be, think of this when you first learn to ride a bicycle. Okay, so you learned how to balance, you learned how to steer, and you have developed spatial awareness. Now in future, if you when you went to learn a bike, okay, so all those knowledge of balance, steering, spatial awareness actually helped you to learn bike faster than if you had learned bike without learning cycling previously before. So this is one example of knowledge transfer that we use without even acknowledging it. Okay, so that's transfer learning in real life, and it's just some similar kind of transformation thing we did here for materials property dataset. So that's all for this tutorial. Thank you.